Introduction to Electrical Circuits, Lecture 1. What is an electrical circuit? It's a mathematical model for how physical circuits operate to transfer energy from one point to another. As we all know, energy can neither be created nor destroyed, but it can be transformed from one form of energy to another form of energy. Again, it can be moved or transferred from one point to another point. Circuit theory can be used to analyze circuits instead of electromagnetic field theory if some assumptions are followed. Some of these assumptions are listed. First one is electric effects are instantaneous, which enables a lumped parameter system model, such as the resistors, capacitors, inductors, diodes, and so on and so forth. The second assumption is that net charge on every component in the system has to be zero. The third assumption is that no magnetic coupling between any pair of systems. When we talk about basic electrical engineering design flow, we will look at the following. First of all, you have a concept, and then you translate your concept into a circuit model or analysis or simulations. And then when the simulation is concluded or you're done analyzing the circuit, you go ahead and produce a physical prototype. And after you have a physical prototype, you validate what you have done by testing it, by carrying out a couple of other processes. And then after the first validation is done, you go to physical design, you go to the real design, the physical design, and then you re-simulate. This simulation is about fine-tuning whatever it is you've done before now, so that you can have a physical product that is dependable and reliable. Once that is completed, you validate the physical design and the second simulation. So the goal of this particular procedure is to minimize the number and extent of leaps from a later to an earlier stage. Invariably, this will go ahead to reduce cost. Once you minimize the loops, that means you're minimizing cost, you're minimizing the bulkiness and the complexity of the circuit. For this particular course, our focus will be on circuit analysis. Basically, that is what we're going to focus on in this particular course. In the laboratory, the focus will be on the physical prototype and the validation of using the prototype, while in the class we'll focus more on the circuit model, the circuit analysis, and the main concept of electrical circuits. Some of the electrical elements that we'll be dealing with would include the diode, the capacitor, the inductor, the resistor, the DC voltage source, the AC voltage source. And what you should pay attention to here are the various symbols for each of these electrical parameters, electrical elements. We'll focus on, first of all, a problem statement. So there will be a problem statement, there will be a theoretical statement that we're expected to analyze, and then there will be a simplified circuit diagram. Either we create it or it's already created alongside the problem statement. And then we pick an analysis method. There will be several analyses that will be discussed in this class. So we'll pick one, the one that is most usable with the problem statement, and then we apply it creatively and see how we can eventually come up with a solution after applying the analysis method. So we calculate a solution at the end of the day, and then we test our solution based on our intuition, or we simulate the solution based on our intuition. So as we proceed, as we go on, our work will focus on understanding how electrical circuits work, and then learning design and analysis using lumped element models. Also, we'll focus on developing theoretical knowledge and practical lab skills useful for characterizing first and second order circuits. And along the line, you'll be introduced to computer-aided design tools for design and simulation work. Now let's briefly talk about charge. Charge is usually represented with Q, just Q if the time is constant, or Q of t if the time is varying. The first thing you should know is that atoms are made up of protons. Protons are usually positively charged. Atoms are made up of protons, neutrons, and electrons. The protons are positively charged, the electrons are negatively charged, while the neutrons they have no charge, they are neutral. A charge can be referred to as being bipolar. That means that it can be positive or negative. And the unit of charge is usually given as coulomb with a symbol C. An electron has 1.6022 times 10 raised to the power minus 9 coulomb. You should be familiar with this. In most of your exams or questions that will be given to you, this value will be provided. In case it is not provided, you can use what you have. So an electron has 1.6022 times 10 raised to the power minus 19 coulomb. 6.24 times 10 raised to the power 18 electrons carry a charge of 1 coulomb. So in this particular case, you need not memorize. All you need to do is if you divide 1 electron by 1.6022 times 10 raised to the power minus 19, it gives you 6.24 times 10 raised to the power 18 electrons at the end of the day. So if you divide both sides, let's say we have 1 electron here, and then we have 1.6022 times 10 raised to the power minus 19 coulomb here. If you divide these by 1.6022, divide these by 1.6022 times 10 raised to the power minus 19, and also here 1.6022 times 10 raised to the power minus 19, what you will eventually find out is that this becomes 1 coulomb here, and this becomes 6.24 times 10 raised to the power 18 electrons. Electric circuits are used to move charges at desired rate through circuit elements. So when we have motion of a charge, we are referring to current. When we have separation of charge, we'll be dealing with voltage. In this particular course, in this particular study, the convention of motion will be positive charge moves to negative charge. For this particular study, positive charge moves to negative charge. Please pay attention to this. It will be used in all our calculations, in all our analysis, in all our simulations. Positive charge moves to negative charge. The law of conservation of charge states that the algebraic sum of all electric charges in a system is constant. Algebraic sum of all electric charges in a system is constant. So we've talked about the structure of an atom. We've talked about all of this. We have said that the electron is assumed to be negatively charged, proton is assumed to be positively charged, while the neutron has no charge at all. Atoms are made up of protons, neutrons, and electrons. We talked about that already. The positive charge moves to the negative charge. This is very important, and it is the passive sign convention that we're going to use throughout this study. Positive charge moves to the negative charge all the time. Let's quickly talk about the current. The current is represented with I when the time is constant, or I of t when the time varies. Current is defined as the time rate of change of charge, and it is given as dq dt. So current is represented with I, and it is given as dq dt, where dq represents the charge and dt represents the time. The unit of current is ampere, which can be represented with A, capital A, and 1 ampere is usually equal to 1 coulomb per second, because as you can see, the Q that represents the charge is measured in coulombs, while the T is measured in seconds. So current can be said to be coulombs per second. That's why we said 1 ampere is equal to 1 coulomb per second. Current has a magnitude and direction, so we always know the direction in which current is flowing. It is possible for us to find out or calculate the total charge entering the element between time 1 and time 2 in the case of having varying time. If the time is not constant, what we use is, we'll say total charge, which is Q total, is given as integral of T1 to T2, integral of I dt from time 1 to time 2, T1 to T2, which will then be equal to Q of T2 minus Q of T1. You know, this is basic and simple integration from your previous studies in the previous years. So, and that's how we got this. All right. So we have direct current and we also have alternating current. The direct current, what you will find out here is that for the change in time, the current remains constant. All right. Current remains constant no matter what the time is. And then for alternating current, as the time varies, you will find that current also varies. The current is sinusoidal. It's like a wave. It has a wave-like motion, so it is called sinusoidal, right? So that's one of the major differences between alternating current and direct current. As time varies, direct current remains constant, and for alternating current, as time varies, the alternating current varies, and it has a sinusoidal motion. Here is a simple example we can quickly look at to demystify what we talked about, the explanations we just gave. Determine charge entering a terminal between 2 seconds and 4 seconds. So T1 is 2 seconds, T2 is 4 seconds. So if the current through the terminal is defined by the function. So what you will find here is that we have a function, a current function given as t squared minus 2t plus 1. And this is a time function. The current is defined with respect to time. So we are expected to find the charge entering a terminal between t equal to 2 seconds and t equal to 4 seconds if the current through the terminal is defined by this function. Okay, the first thing we want to do is to go to the equation I gave us that has to do with varying times. That will give us charge will be equal to integral of I dt from t1 equal to t2, from t1 to t2. So t1 is 2, t2 is 4. So we have t equal to 2 to 4 I dt. Our I is t squared minus 2t plus 1. What you need to do is just insert that integral function and then you integrate. When you integrate, you have t squared. When you integrate, you have t cubed over 3 minus t squared plus t. This is again simple integration. You may need to go and brush up your integration skills so you can follow up with what we're talking about here. So once you do that and you substitute T2 and T1 into this integrated solution, what you have is 8.667 coulombs. So the charge entering a terminal between t equal to 2 seconds and t equal to 4 seconds is equal to 8.667 coulombs if the current through the terminal is defined by this particular function. Let's quickly talk about voltage. Voltage is represented as V if the time is constant and V of t if the time varies. Voltage can be referred to as electromotive force or potential difference between 2 points, A and B, and that voltage is the energy needed to move a unit charge from point A to point B. So we can say voltage between point A and B is represented as VAB. VAB will be equal to dW dQ, where W represents the work done or energy. All right, W represents the work done or energy. So voltage between point A and B, the voltage between point A and B will be equal to dW dQ. Q represents the charge, W represents the work done or energy. The unit of voltage is going to be equal to volt, and since we said W is work done or energy, that will be joules, Q is coulomb. So 1 volt will be equal to 1 joules per coulomb. 1 joules work done is usually given as force times distance. Force is newtons, distance is meters. So you find out that 1 joules is the same thing as 1 newton meters. So the entire expression can also be written as 1 volt equals 1 Newton meter per coulomb. So the conventions that we're going to be dealing with in this course, as you can see here, we have two terminals. This is terminal A. You can see a terminal here. There's another terminal here. V0 represents our voltage, and you can see positive and negative charges here. So if we have terminal A and then we have terminal B, the voltage across this element we have here between these two terminals will be given as VAB. The voltage between these two terminals will be given as VAB. All right, this is the convention we are going to use in this course for all our calculations and analysis. When energy is consumed by the circuit element, this is the circuit element given here. When energy is consumed by the circuit element, we see that current is flowing from the positive charge to the negative charge. This is important. No matter how the structure, no matter what the structure of the system looks like, if energy is consumed by the circuit element, current always flows from the positive charge to negative charge. All right, and then if you find out that current is flowing from negative charge to positive charge, it simply means that energy is delivered by the circuit element. This is very important. So you can see current flowing from negative to positive, also here from negative to positive. So this means that energy is delivered by the circuit. So we've talked about this convention. Let's quickly look at the passive sign convention. When the current through an element is in the direction of the reference voltage drop across the element, a positive sign should be used in expressions relating the voltage to the current. So what you will find out here, let's quickly explain that. So we said energy consumed, when energy is consumed by the circuit element, current flows from positive charge to negative charge. So the voltage here will be equal to plus, because current is flowing from positive to negative. So whatever function we have here as a function of current, it could be current multiplied by resistance or current multiplied by anything, this will be a positive sign because current is flowing from positive to negative. Voltage will be equal to positive. The voltage will be positive, whatever the function is here. Okay. And when current is flowing from negative to positive charge, it simply means energy is being delivered. Energy is delivered by the circuit element. In that case, voltage will be negative. All right. So when current flows from negative to positive, current is going from negative to positive, is going up here, as you can see from this second diagram. It means energy is delivered by the circuit element, and our voltage will take on a negative polarity. It will be negative here. We are assigning negative value to the voltage. Okay, so please pay attention to that. These are standard prefixes for powers of 10. You can see we have 10 raised to the minus 18 down to 10 raised to the minus 2, and you can see the various prefixes. Centi is 10 raised to the minus 2, so that's probably centimeters if we are dealing with meters. We have milli, if we're dealing with meters, we have millimeters, 10 raised to the minus 3, micrometers, 10 raised to the minus 6, right up to atto, which is 10 raised to the minus 18. You can see there are various symbols here, C, M, micro, nano, and so on and so forth. And then you can also see we have 10 raised to the minus 1 down to 10 raised to the minus 1 is deci, 10 raised to the 12 is tera, 10 raised to the 9 is giga. You can see G, 10 raised to the 9 is giga. You can see G, mega is 10 raised to the 6, kilo is 10 raised to the 3. You should be familiar with these standard prefixes for the powers of 10. They will be useful for you and for us in our studies. So let's briefly talk about power. Power can be represented with a symbol P when the time is constant, and then it can be represented with P of t if the time varies. Power is defined as the rate at which work is being done. So we can say power is dW dt. Power is going to be the rate. Rate talks about time, so we have work done over time. And the unit of power is joules per second. Since work done is joules and time is seconds, the unit of power would be equal to joules per second, or it could be equal to watt. In that case, we can say 1 watt is equal to 1 joule per second. So power is equal to dWt, as you can see here. This can also be written as dW dq times dq dt. All right. So if you calculate, if you delete this dq and dq, because they will cancel out, you will have our dw dt back, because the identity of the dw dt is being kept when we cancel dq, these two dqs, when they cancel out. So since they are the same, we can then say this will be equal to v dq dt. Where is this v coming from? Don't forget, we said our voltage is dw dq. We also said our current is dq dt. So that simply means that you can represent both of them. Represent dw dq with v, represent dq dt with I, and then your power will eventually be equal to v multiplied by I. Power will be equal to vi at the end of the day, which is voltage multiplied by current. Energy delivered to an element between time 1 to 2 can also be calculated, can be obtained. So you use our integral function to do that. When we have time from point 1, when we have time 1 and time 2, and we have energy being delivered to an element from that time 1 to a time 2, work done or energy can be calculated as follows: power dt from time 1 to time 2, and that will give us, since we know our power to be equal to vi, you replace p with vi from time 1 to time 2 dt, and then when you integrate these using our understanding of integral functions, you have wt2 minus wt1 at the end of the day. That is what you're going to have when you integrate these. So this is how to find energy delivered to an element between time 1 and time 2. So our conventions for power in a circuit, we have to understand that total power, the sum of all the power in a circuit, is equal to 0. Has to be equal to 0. Please pay attention to that. Also, the element is consuming power. A circuit element is consuming power when current moves from positive charge to negative end of the circuit, negative terminal of the circuit. When current flows from the positive terminal of the circuit to the negative terminal of the circuit. So we say the circuit is consuming power, which is the same thing that we've been talking about. And in this particular case, the element, the convention will be positive. Yeah. All right, and then when current is moving from the negative charge to the positive charge, we say the element is delivering power. In this particular case, the convention will be negative. Power will be negative. So when you are finding power and you notice that current is flowing from positive to negative, your power will be equal to VI. That is going to be equal to positive power. And then when you notice that the current is flowing from negative charge to positive charge, the convention for power would be negative. So you have minus VI. Please pay attention to these two. Here is an example we can quickly demystify together. A stove draws 10 ampere when connected to a 120 volt line. How long does it take to consume 30 kilojoules? So we have 10 ampere, that's the current. We have 120 volt, that's the voltage. We have 30 kilojoules, that's the energy. So we are expected to find the time. How long does it take to consume 30 kilojoules? This is the solution. We do know that power is equal to voltage times current. Our voltage is 120, our current is 10 ampere. So when you multiply those out, what you'll find is 1200 watts, which is the same thing as 1.2 kilowatt. Because we said that kilo is 10 raised to power 3. So when you divide this by 1000, you have 1.2. This gives us 1.2 kilowatt. Energy is usually equal to power times time, or power is equal to energy over time, or time is equal to energy over power. So since we know that energy is equal to power times time, and we can rearrange it to say that time is equal to energy over power, that simply means the energy we have, which is 30 kilojoules, can be divided by the power we've calculated of 1.2 kilowatt. 30 kilojoules is the same thing as 30 kilowatt seconds, because we said 1 joule per second is equal to 1 watt. So we can also say that 1 joule will be equal to 1 watt times seconds. So since we have 30 kilojoules here, these joules can be replaced with watt seconds. So we can have 30 kilowatt seconds. Kilowatts will cancel kilowatt, and then you are left with just seconds. So 30 over 1.2 is 25, and then the time will just be equal to 25 seconds. So a stove draws 10 ampere when connected to 120 volt line. It will take 25 seconds to consume 30 kilojoules when we have a system like this. A notebook computer has a total power consumption of 50 watts when running an average application. The battery used in this notebook has a capacity of 300 watt hours. What is the average battery life of this notebook? This is also straightforward. We know that our time is equal to energy over power. All right, energy for a battery will be equal to the battery capacity, and we have been given in the question that the battery capacity is 300 watt hours. So you can put 300 watt hours here divided by the power consumption, which is 50 watt. When you do that, you have 6 hours left. 300 over 50 is 6. Watt will cancel watt, and then we have hours left. So the total time, the total average battery life, which would be in terms of time, is going to be equal to 6 hours for the notebook computer. So watt hours can be used as a unit of energy instead of joules. We mentioned this earlier, by the way. So one joule can be equal to watt hours. The energy absorbed by a passive element up to any time t must be non-negative. This is also very important. So what you see here is that energy will be equal to minus infinity to time t. Let's say energy, is coming from minus infinity, power dt. So this is p of t dt, okay? And this is going to be given as vi because our power is vi. The energy absorbed by a passive element up to time t can never ever be negative. It must be greater than or equal to 0. And then this is also, true for active elements. The opposite of this is true for active elements. For passive elements, the energy must be greater than or equal to 0. The opposite is true for active elements. It must be less than or equal to 0. Some of the active elements we do have are the independent voltage source. This is important, independent voltage source or independent current source. So you will find out that a voltage source is represented with Vs, and what you can see here, we have a circle here with positive and negative polarity in that particular circle, as you can see here, or we have this. So this is an independent voltage source. In this particular case, the voltage is fixed no matter what the value of the current is, in the case of independent voltage source. Then we have the independent current source. As you can see, we have a circle, and then we have an arrow in that particular circle. It is represented with Is. So current is fixed irrespective of what the value of the voltage is in this case. So this brings us to the end of this particular class. See you in the next class. Thank you.